So what we have here is a colorized pair of merging galaxies. My laptop screen hardly does it justice, but I hope that gives you a sense of scale of what we're looking at, even nightly.
For decades, we've had a story about how everything came to be. It's a story of a slow, patient universe where galaxies, stars, and even us took billions of years to form. But what if that story is wrong? Once again, the Webb telescope has delivered a jaw-dropping discovery from the dark, quiet corners of the early universe, something that simply shouldn't exist. And it has scientists genuinely worried that we might have to rewrite the entire history of the cosmos. The standard story of everything. To truly grasp what's at stake here, we need to take a quick step back in time, about 13.8 billion years to be exact. The story we've long told ourselves is called the Lambda Cold Dark Matter Model, or LCDM for short. For decades, it's been the bedrock of modern cosmology, a grand narrative that explains everything from the faint afterglow of the Big Bang to the vast, web-like structure of galaxies we see today. The story begins in a universe that was an incredibly hot, dense, and almost perfectly uniform soup of particles. But as it expanded and cooled, tiny, almost unnoticeable fluctuations in density started to take shape. These were the seeds of everything that would ever exist. Here's where the cold, dark matter part of the theory becomes crucial. Dark matter is a mysterious, invisible substance that doesn't interact with light, but it has gravity. According to our standard model, this invisible matter created the universe's first scaffolding. The tiny, denser-than-average patches of dark matter began to gravitationally pull in more dark matter, creating enormous, invisible clouds called halos. From there, we believed the process was slow and methodical. Think of it like tiny snowflakes gently clumping together to form a giant snowball. Ordinary matter, the stuff of stars and planets, was gradually pulled into these dark matter halos. It slowly cooled, condensed, and ignited into the first small primitive stars and galaxies. Then, in a process called hierarchical clustering, a small galaxy would merge with another, and that new, bigger galaxy would merge with another, and so on, over billions of years. Our own Milky Way is a product of this cosmic consumption, having swallowed countless smaller galaxies over its lifetime. Under this model, the universe took its time. The first few 100 million years should have been relatively quiet, the cosmic dark ages. The first truly massive, well-organized galaxies weren't expected to show up until the universe was at least a couple of billion years old. It takes time to gather matter and organize it into the majestic spiral shapes we see today. This was the settled science. At least, that's what we used to think. The Universe Breakers. Launched on Christmas Day, 2021, the James Webb Space Telescope is the most powerful time machine ever built. Its massive gold-plated mirror was specifically designed to look back to the cosmic dawn, to find those first, faint baby galaxies that our models predicted should be there. But that's not what it found. Almost immediately, the data started pouring in, and astronomers were stunned. Peering into the cosmic dawn, a period just 500 to 700 million years after the Big Bang, Webb saw galaxies that were, to put it mildly, impossible. These weren't the small infant galaxies everyone was expecting. They were monsters. In what should have been a cosmic nursery, Webb was finding fully grown adults. These galaxies were already packed with billions of stars, some rivaling the mass of our modern-day Milky Way. They were so paradigm-shattering that astronomers started calling them universe breakers. One of these early behemoths, a galaxy named GZ9P3, was seen as it was just 510 million years after the Big Bang. To the Hubble telescope, it was just a faint dot, but Webb's powerful vision revealed it was already 10 times more massive than any other galaxy confirmed from that era. Even more shockingly, it had a complex shape suggesting it was already the product of two galaxies merging, a process that was supposed to take much, much longer. And as if that weren't enough, another discovery from May 2025, dubbed MOEM-Z14, pushed the boundary even further. This galaxy was spotted just 280 million years after the Big Bang, when the universe was barely 2% of its current age. According to standard models, bright, well-formed galaxies simply shouldn't exist so early. The discovery implied that such objects could be over 100 times more common than our theories predicted. It wasn't just a fluke, it was a fundamental challenge. The deeper Webb looked, the less time our theories had to explain what it was seeing.
The contradiction. Why scientists are worried. So, what does this actually mean? Why is finding big galaxies so early a problem? It's like an archaeologist finding a fully functional smartphone buried in a sealed ancient Roman tomb. It's not just surprising, it fundamentally contradicts everything you thought you knew. The standard Lambda CDM model is built on a budget of time and matter. There was only a finite amount of gas available to form stars, and a limited time for gravity to pull it all together. The model's predictions are quite strict. In the early universe, star formation should have been a slow, inefficient process, with at most 20% of available gas in a halo turning into stars. The galaxies Webb found completely obliterate that budget. To form a galaxy as massive as the Milky Way in just a few 100 million years requires a level of efficiency our models simply can't explain. The stars must have formed far more rapidly than anyone thought possible. It defies the known laws of cosmic growth. This is the heart of the cosmology crisis. It has forced scientists to question two pillars of our understanding. Either the physics of how galaxies form is wrong, or the Lambda CDM model itself is incomplete. The first possibility is that the early universe was far more exotic than we imagined. Maybe the first generation of stars, so-called population 3 stars, were colossal giants that burned through their fuel in a cosmic blink, seeding the universe with heavy elements far faster than our models predict. Or perhaps the supermassive black holes at the center of galaxies formed much earlier, acting as powerful cosmic anchors that rapidly accelerated galaxy growth. Some recent research has offered a less dramatic explanation. Studies published in late 2024 suggest some universe breakers might not be as massive as they appear. The intense light could be from gas being furiously consumed by a central black hole, making the galaxy appear much brighter and more massive than it really is. This would solve the problem for some galaxies, but not all of them. Even when these objects are accounted for, there are still about twice as many massive galaxies in the early universe as the standard model predicts. The problem is lessened, but it hasn't gone away. This leads to the second, more profound possibility, that the standard model of cosmology itself is wrong. What if dark matter doesn't behave the way we think? Some researchers have pointed out that these findings align better with a controversial alternative theory of gravity known as MOND, which predicts that cosmic structures would have formed much more quickly. Other, more radical ideas, like the universe being much older than 13.8 billion years, are also on the table, highlighting the sheer scale of the challenge Webb has presented. The implications: rewriting the textbooks. When a discovery challenges a theory as foundational as the standard model of cosmology, it's not just one chapter of the textbook that needs a revision, it might be the entire book. If the problem isn't just an illusion from bright black holes, scientists are forced back to the drawing board. One of the first places they're looking is at the initial conditions of the universe. To get bigger galaxies faster, you might need bigger density fluctuations right after the Big Bang. But changing this is a delicate balancing act, as any new model must still match the incredibly precise map of the early universe provided by the cosmic microwave background. The nature of dark matter and dark energy is also under intense scrutiny. The standard model assumes dark matter is cold and slow-moving, allowing it to clump together. But what if its properties are more complex? Likewise, it assumes dark energy is a constant, but some theorists now speculate that if it was different in the early universe, it could have allowed structures to form more quickly. The very process of star formation is being re-examined. The red monster galaxies discovered by Webb appear to have formed stars with breathtaking efficiency, nearly twice as fast as galaxies in the later universe, a finding current models struggled to explain. Each of these potential solutions would represent a major shift in our understanding. The revelation that massive galaxies were common so early upends what many thought was settled science. The tidy, bottom-up story of galaxy formation is being replaced by a more chaotic and accelerated narrative, one that we are only just beginning to piece together. Beyond galaxies, a universe of puzzles. And as if that weren't enough, the list of baffling cosmic anomalies from Webb keeps growing. Its powerful gaze has revealed other puzzles that hint we are entering a new era of physics. For instance, it has observed mysterious, perfectly concentric rings around a distant star named WR140, a phenomenon that doesn't neatly fit our current models of how stars work. It has also detected complex organic molecules in the coldest, darkest clouds of space, suggesting the building blocks for life are more common than we thought. On a more speculative note, Webb's power has ignited debate about life beyond Earth. You may have seen viral claims that the telescope detected artificial lights on Proxima b. To be clear, these claims are unconfirmed, and there is no credible scientific evidence to support them. However, the very possibility that Webb could detect industrial pollutants has shifted the search for alien technology from pure science fiction to a tangible scientific pursuit. Each of these discoveries, from impossible galaxies to faint chemical signals, point to a single, overwhelming conclusion. The universe is more complex, more surprising, and stranger than we ever imagined. These aren't just isolated puzzles, they are a pattern. They are the cracks appearing in a long-held paradigm, hinting at new physics waiting underneath. The James Webb Space Telescope was built to answer our oldest questions, but instead it has given us a host of new ones, challenging the very foundations of cosmology. The discovery of galaxies that are too big, too bright, and too early has sent a shockwave through the scientific community. It's a beautiful, thrilling, and deeply worrying problem. While some of these universe breakers might be a cosmic illusion, the anomaly hasn't vanished. We are still left with more massive galaxies than our best theories can explain. We are at a crossroads. We must either fundamentally revise our understanding of how galaxies are born, or confront the possibility that our standard story of the universe is missing a key chapter. But this isn't a failure of science. It is the greatest triumph. It is the moment when a new instrument pushes us beyond the horizon of our knowledge and reveals that the map we've been using is incomplete. The story of the universe didn't end with the Lambda CDM model. As Webb continues to stare into the cosmic dawn, we can be sure of one thing. The universe is not done surprising us, and the next discovery might just change everything.